അസാപ്പിന്റെ ഓൺലൈൻ സെഷൻസിലേക്ക് സ്വാഗതം. ഇന്നത്തെ സെഷൻസ് കൈകാര്യം ചെയ്യുന്നത് ജെഎസ് ജോർജ് ജോസഫ് ആണ്. സർ സുൽത്താൻ ബത്തേരി സെന്റ് മേരീസ് കോളേജിലെ അസിസ്റ്റന്റ് പ്രൊഫസറാണ്. സർ ഇന്ന് ചെയ്യാൻ പോകുന്ന വിഷയം ക്വാണ്ടം മെക്കാനിക്സിലെ തിയറി ഓഫ് ആംഗുലാർ മൊമെന്റം എന്ന സബ്ജക്റ്റ് ആണ്. സാറിനെ കുറിച്ച് പറയുകയാണെങ്കിൽ സർ 10 വർഷത്തോളം എക്സ്പീരിയൻസ് ഉള്ള ഒരു പ്രൊഫസറാണ്. 10 വർഷമായി അണ്ടർ ഗ്രാജുവേറ്റ് ആൻഡ് പോസ്റ്റ് ഗ്രാജുവേറ്റ് സ്റ്റുഡൻസിനെ പരിശീലിപ്പിക്കുന്നുണ്ട്. സാറിന്റെ ഏരിയ ഓഫ് റിസർച്ച് എന്ന് പറയുന്നത് ന്യൂക്ലിയർ ഫിസിക്സിലാണ്. 5 ഇന്റർനാഷണൽ പേപ്പറുകൾ കണ്ണൂർ സ്വദേശിയായ സർ കൈകാര്യം ചെയ്തിട്ടുണ്ട്. അത് സർ പബ്ലിഷ് ചെയ്തിട്ടുണ്ട്. സ്റ്റുഡൻസിനുള്ള ജനറൽ ഇൻസ്ട്രക്ഷൻസ് പ്രൊവൈഡ് ചെയ്യാൻ പോവുകയാണ്. ഞാൻ സെഷൻ തുടങ്ങുവാനായി സാറിലേക്ക് കൊടുക്കുകയാണ്. സർ, യു ക്യാൻ സ്റ്റാർട്ട്.
Okay. Today we are going to discuss theory of angular momentum. Now we are going to discuss a small introduction regarding this theory of angular momentum. Theory of angular momentum in quantum mechanics is more important by following reasons. One is, in quantum mechanics, angular momentum is quantized both in magnitude and orientation in space. That means it has discrete values, not to take continuous values as in classical mechanics. The concept of angular momentum in quantum mechanics is not only limited to rotatory motion, but also it is the generalization of quantities like spin and isospin. And spin is the intrinsic angular momentum of a particle. Example is the spin of electron is 3/2 h cross, where h cross is the unit of angular momentum in quantum mechanics. And isospin is a quantity representing particle multiplet. As an example, proton and neutron are two isospin state of a single entity called nucleon. So nucleon is a doublet stage. In quantum mechanics, the concept of periodicity and periodic motion happens frequently, and it is related to rotatory motion and the angular momentum. This is a brief introduction regarding this theory of angular momentum. And now we are going to discuss non-commutative nature of rotation about different axes. Let us consider two consecutive rotations of a rectangular box in different manner. Here case 1 is two successive rotations about a single axis in counterclockwise direction. When the angle is positive, here let's see, if you take the counterclockwise rotation, angle is positive. That is a convention. And here the rotating axis is taken as a z-axis. Here the first rotation is labeled as rz of phi1, and second rotation is labeled as rz of phi2. And here that is the suffix z denotes axis of rotation, and phi1 and phi2 denote the angle to which it rotated. Now we perform two rotations in two different orders. In the first order, a 30-degree rotation followed by 60-degree rotation, and in the second order, a 60-degree rotation followed by 30-degree rotation. And it is depicted in our figure. And here this is the first the states, and here there is a rectangular box that is horizontally placed, and then it rotate about this z-axis in counterclockwise direction by an angle 30 degree, and its position is denoted as a 2. And then again it rotates counterclockwise direction about the z-axis, and then its the final state is denoted as a 4, and at that position this object stand erect. And this is the first step. And in the second step, we are reversing the order. That means initially we are rotating about the z-axis, the counterclockwise, an angle 60 degree, and then rotate 30 in counterclockwise, and then the state is the same as before. It means that the two positions are identical. So we can write from this, we can write RZ 30 into RZ 60 is equal to RZ 60 into RZ 30. Or we can write this RZ of phi 1 into RZ of phi 2. Here this the phi 1 is 30 and phi 2 is 60 is equal to RZ of phi 2 into RZ of phi 1. Or we can write RZ of phi 1 into RZ of phi 2 minus RZ of phi 2 into RZ of phi 1 is equal to 0. Or a square bracket, within the square bracket we are writing RZ of phi 1 comma RZ of phi 2 is equal to 0, where the square bracket. Here there is a small note regarding this commutator bracket. A comma B, read as the commutator A comma B, and it is equal to AB minus BA. If A comma B, commutator A comma B is equal to 0 means AB minus BA is equal to 0, or A commute with B. So from our example, we can just say that two rotations about a single axis will commute among themselves. This is the second case. And here again, we consider two successive rotations, but in two different axes. In first case, rotation about the z-axis by an angle 90 degree, then followed by about x-axis by 90. In the second case, a rotation about x-axis followed by the z-axis, as in this figure. And this is our second experiment. And here there is a rectangular box, as like a book placed in a horizontal surface. And this the vertical axis is taken as a z-axis. And now we are rotating this object anti-clockwise direction about the z-axis, an angle 90 degree. Then this is its position, that is the second position. And again we are rotating that object counterclockwise direction about x-axis. Then this is the last, that's the last position in the first row, that is the final position of that object. And in the second experiment, and the second part, that is we are reversing that order. Instead of the rotating initially in the z-axis, we are rotating about x-axis by an angle 90 degree. And then again rotate counterclockwise direction about the z-axis. And then this is the final position that is mentioned in second row, last one. So comparing that two, that is we can see that the two final positions are not identical. Here we have noticed that these two final states are not identical in orientation. So we can write RZ 90 into RX 90 not is equal to RX 90 into RZ 90. Or we can write RZ 90 into RX 90 minus RX 90 into RZ 90 not is equal to 0. Or RZ90 the commutator RZ comma and RZ comma RX not is equal to 0. So from this we can conclude that rotation about two different will not commute among themselves. And here we are going to discuss some special cases. And the first case is, if the rotation about each axis is very small, then the final state are identical. So you can perceive it by taking a book and rotate it about two perpendicular axes in succession and notice the files. Then the repeat again in other order. Then you get. So that means, as an example, I am taking a small object about, and here this axis and this axis is taken as its x-axis, and initially I am rotating a very small angle about this is z-axis, like this is the position, and then rotate about x-axis like this. And if you perform this again in reverse order, that means initially rotate in x and then rotate in z, this, and these the two positions are identical. It is clear that if the angle is very small, the rotation is commuting, and to what extent rotates, what is the angle at which that is that the show the symmetry, that we will discuss in the coming section. And the second is, there is a second case, if the object is symmetrical either by any of rotation, then it will commute. It is you get it by taking an object having cylindrical symmetry and consider one rotation is about a symmetry axis, and here there is a simply I am taking an object like this, and here about is this axis, that is axis along the length, it is the symmetry. And so if I am initially performing a rotation about the z-axis like this, and then I perform a rotation about this symmetry axis, and if you reverse that order, that is initially we are doing rotation about symmetry axis and then rotate the z-axis, that these two are identical. So here there are the two special cases are there in which the rotation commute among themselves. As a conclusion from the above observations, we can say that if the rotation is about the single axis or infinitesimal rotations about a different axis, or system has the some simultaneous rotation, then your rotations will commute. In the case of finite rotations along the different axes, they will not commute among themselves. And when we speak generally, rotation operations will not commute among themselves. That is, we can write this commutator of Ri, Rj not is equal to 0, where I, j denote axis x, y, and z. You can take any of two axes as I and j, and that quantity not is equal to 0. This is the general expression. But here we found that in some special cases, as like infinitesimal rotation or the rotation about the same axis, and at that instant it will commute. Otherwise, generally the rotation will not commute among themselves. Now we are going to discuss a quantitative measurement of a mismatch, and here we are going to determine the quantitative measure of mismatch between the rotations that happened into different orders. That is, Ri phi1 comma Rj phi2 is equal to what? What extent these the two are deviating? Initially we are taking R, that means Rx Ry minus Ry Rx is what? That quantity we want to determine. It's a quantitative measurement of that mismatch. To do this, we consider the following procedure. Initially, we consider effect of rotation on a vector v having components Vx, Vy, Vz in a three-dimensional space. So here we are considering a vector in our ordinary three-dimensional space. And if we rotate coordinates, the components of the vector will undergo variations, and the resulting components can be written as Vx prime, Vy prime, Vz prime. That means this is the transformed. That is, the prime is the denoting transformed is equal to R into Vx, Vy, Vz. And here R is a 3 by 3 matrix. And here that the initial vector components we are expressed in the form of a column matrix. And the final state is also a column matrix. R is a matrix and its dimension is 3 by 3. And now we are going to check the nature of this transformation matrix R. R is the transformation matrix, the initial coordinate to the final coordinate. Let us consider rotation of a coordinate system about the z-axis as in figure. And here the z-axis is not mentioned in this figure, and the direction is the perpendicular to the plane of this paper. That is the direction of the z. And it is the rotating the some angle, that is say phi. That is the angle of rotation is taken as a phi in anti-clockwise way. And then the new coordinate is denoted as x prime and y prime. And x prime and y prime and the new coordinate. And v and w are two vectors in this space. This is two vector. So two ordinary vector, and that is taken as a v and w. The property of rotation operation is that the length and the angle between the vectors remain unchanged. That is the property of the rotation, and that you can see from the previous slide. That is, if you rotate this the coordinate x and y, that reaches to x prime and y prime, but that is a vector remain there, and is the angle between that vector remain unchanged. So this the property of rotation operation is that the length and the angle between the vectors remain unchanged. That is mentioned that denoted in figure. And length and angle between vectors that remain unchanged means the dot product of a or inner product or scalar product of these two remain unchanged. And that three are using to represent a single name, single entity. That is, either you can say dot product or inner product or scalar product, but that is the inner product is the more general. But to understand it more easily, I took that other two, that is dot and scalar. There is a dot. Scalar means this the result of this the product is a scalar quantity. So when we take this inner product or the scalar product, the result is the resulting quantity is a scalar. Generally, it is a complex, but here we are discussing in our three-dimensional ordinary space. Then it is a real quantity. So here that is the inner product. Here that is the scalar product of this. That is in way we can write v vector v into w is equal to, there is a transformed vector, that is v prime into w prime, or that is in the writing the two vertical line in between the two vector we are taking it as a single. There is a vw is equal to v prime w prime. And that's the primary is the denoting transform. All entire in this the lecture. That is a primary is the denoting transform, unprimary is denoting original. Okay, that's equation number 3 denoted. And here v prime is equal to r into v, where r is our the transformation matrix. And bracket, that is a con bracket, is using to denote vector, and it is called as a Dirac-Petit notation. As in equation 2, the vector is represented by a column matrix. So we are going back, and then initially we wrote that the matrix in the form of a column matrix. So there is a vector is represented by a column matrix. So here the Dirac-Petit is a column vector. The value of inner product is always a scalar. It's already said. In the case of inner product, is the value is a scalar. So the nature of the vector that that written on the left side, it will be taken as this way, and it should be a raw matrix. So when we are a raw matrix into a column matrix only lead to a scalar count. So the nature of that vector we wrote on the left side is a row and the right is a column. Generally it is called, and that will be called as Dirac-Bera vector, and more precisely that Dirac-Bera we termed as it's a dual of 𝐻. Okay, that is the more exact the definition. That is the dual of that one. For we can write that is a bra vector v prime is equal to bra vector v into r prime rt, and where rt is the matrix R. In equation we have used the property of matrix, that is AB transpose is equal to B transpose into A transpose. And here V prime, and here this V prime, that is the bra prime, is obtained by the taking the transpose. So here we have the taking transpose on both sides. This transpose is equal to all transpose, R of V all transpose, that is equal to V transpose into R transpose, and this ket transpose is equal to, that is a bra. That is the thing, that is V into R transpose. And the substitute equation 4 and 5 in equation 3, we get this is the V M, that is the inner product V W is equal to V prime W prime, that is unchanged. This is equal to, that is V prime is equal to V R transpose, and W prime is equal to R W. This is the quantity. Compare LHS and RHS of above equation and compare these two. We get R transpose into R is equal to 1, where 1 is the identity operator. It is not the single scalar one, it is an operator, or it is a matrix. This is a matrix. And this is condition for orthogonality of matrices. So we can say the rotation matrix is orthogonal. Although this is the concept of orthogonal. In the case of a transformation orthogonal, that means in the case of an orthogonal transformation, both the length and the angle between the vectors they remain unchanged. So if you consider some object like and this object, and if you consider the axis on all the sides of this object, and if I do a different operation like the rotation or translation or reflection or whatever, and both the length and the angle between that the vectors they remain unchanged. So that kind of a transformation is termed as orthogonal transformation, and it's the condition is, and the corresponding the transformation matrix nature is R into R transpose is equal to 1, that is equal to R transpose into R. When basis of a coordinated system rotate an angle phi about the z axis in anti-clockwise direction, then the corresponding transformation matrix is. And this is the corresponding transformation matrix. That means the here, and this the matrix is the rotation matrix corresponding to the rotation of a coordinate system about the z axis. We rotated that coordinate system about the z axis. So the rotation is about the z axis, therefore the z component will remain unchanged there. Therefore that is the last one. And other x and y component will change, and it varies like this way: cos phi, sin phi 0, minus sin phi, cos phi 0, 0, 0, 1. Okay, that is the you can do simply the plotting a figure, and then determine the corresponding change in the component value, and that is the change in component is a direction cosine between initial and transformed coordinate. That way we are doing. It is already familiar to you. And that is this is that matrix corresponding to a transformation. This kind of a transformation is termed as a passive transformation, that is transformation of coordinates. The other kind of transformation called active transformation. Here the system, here the vector V. This is here the system we consider as that vector V undergoes the rotation phi in anti-clockwise direction. The rotation of the system in anti-clockwise direction through an angle phi is the same as rotation of a coordinate about the same angle in clockwise rotation. Here angle is but here I consider that this is the thing, and here this is the two coordinate system taken as x and y. And here this is the our system vector, or that is our vector. It becomes this is the vector. And there are the two kinds of the rotations are possible. One is you can rotate this vector itself. And this is I am rotating here the anti-clockwise in this direction. This is the one possibility. And this kind of transformation is termed as active transformation. And in this active transformation, the system itself is rotating. And in the passive transformation means the system keep at the position here itself, but this the coordinate will rotate this way. And so if you consider these two cases, then here this is we consider the rotation of the system by an angle phi anti-clockwise direction. And so here it is initially set here, so here it is initially, and this is rotated to this is the final position, and this is the state. And this is the same as this is the initial state, rotating the coordinate system clockwise the same angle. Therefore, these two are same. Okay. So here what we said is the rotation of the system in anti-clockwise direction through an angle phi is the same as rotation of the coordinates about the same angle in clockwise direction, and the clockwise direction rotation conventionally taken as a negative. To get the corresponding rotation matrix, substitute phi is equal to minus phi in equation 6. And here, and substitute this phi is equal to minus phi here, then we get the transformation matrix the corresponding to active rotation. So that is this one. R set of phi is equal to cos phi, and if cos of minus phi is equal to cos phi itself, but the cos sine of minus phi, that is a minus sine phi. And so that is the minus sine phi 0, sine phi, cos phi 0, 0, 0, 1. It is equation 7. And that is the represents the transformation matrix corresponding to active rotation. In quantum mechanics, we are interested generally in the transformation of the system rather than coordinates. That is the active transformations. Now consider an infinitesimal rotation through an angle phi. That is taken as, that is infinitely small angle phi that is taken as a epsilon. Then cos phi is equal to, cos epsilon is equal to 1 minus epsilon square by 2 factorial plus epsilon raised to 4 by 4 factorial plus etc. And that is nearly is equal to 1 minus epsilon square divided by 2 factorial. We are limiting with the first that 2 times because the epsilon here is very small. And all the higher order powers are effect is very small, therefore we are neglecting. And sine phi, and here we use the expansion of a cos and sine. And similarly, sine phi is equal to sine epsilon. This is equal to epsilon minus epsilon cubed by 3 factorial plus epsilon raised to pi by 5 factorial minus etc. That is nearly is equal to epsilon. And here it means in these two, we limited up to the power of epsilon square. Are limited up to the power epsilon square, and all other higher orders we neglected here. And here we are limiting the expansion up to epsilon square, and substitute the above value of the sine and the cosine in equation 7, we get r sub of epsilon is equal to, and the first term is there is a cos, there is a 1 minus epsilon square by 2, and this is the minus sine, therefore that is become as minus sine theta is equal to theta. And so minus theta, that is minus epsilon 0. And here this is a plus sine theta, that is epsilon itself. And here this is 1 minus epsilon square by 2, 0. The last is 0, 0, 1. Similarly, the rotation matrix corresponding to other axes can be written as. That is, instead of taking Z, we consider other two axes, that is X and Y. That is the Rx of epsilon. And here, if the rotation is above the X axis, then the corresponding X component will remain unchanged. That is 1. And Y and Z will change as like before. And that is the corresponding values of this one. 1 minus epsilon square by 2 minus epsilon. And 0 epsilon 1 minus epsilon square by 2. And Ry of epsilon is equal to, here also, this is the Y that will remain unchanged. So that matrix you can write in this form. It's 1 minus epsilon square by 2, 0 epsilon, 0, 1, 0, minus epsilon, 0, 1 minus epsilon square by 2. Now from equation 8 and 9, by limiting the term up to epsilon square, we get, initially we have to determine this quantity in order to check the commutation relation. And here this is a Rx of epsilon, Ry of epsilon, that is equal to, its Rx of epsilon is this matrix, and this is the Ry of epsilon, and its the product is equal to. So we are multiplying this the row, first row is along with the first column of the second matrix. And so this is 1 into 1 minus epsilon square by 2. That quantity is 1 minus epsilon square by 2 plus, and the other two quantities goes to 0. Therefore, the first element is 1 minus epsilon square by 2. And the second element is obtained by again the multiplying the first row with the second column. And here this the first element is 0, second element is 0, also third element is also here 0. And so that is this is the second element here, this is 0. And in third, to determine the element of third element in the first row, we are again multiplying this the first row in the third column. That is equal to 1 into epsilon is equal to epsilon, and the other two are 0. Therefore, that element is epsilon. And now we are going to determine the second row elements. It is 0 into 1 minus epsilon square by 2, that is 0. Here, this is a second is 1 minus epsilon square by 2 into 0, that is again 0. And the third is minus epsilon into minus epsilon. And here, that is minus, that is a epsilon square, this element. And then here, this be determined by again multiplication, that is 0 plus 1 minus epsilon square by 2, that is that element. And last, that is 0. And the final element of second row is multiplied by that second row and last column, that is equal again, that is 0, 0. And that is a minus epsilon, that is multiplication minus epsilon cubed by 2 will result. But we are eliminating all the power greater than square. Therefore, we are eliminating the last 10, therefore the minus epsilon itself. And the final row element is first is minus epsilon, and the second is epsilon, and the last is that is 1 minus epsilon square. And this is the product value of that two matrices. And then now we are doing that multiplication in reverse order. There is a Ry of epsilon, Rx of epsilon is equal to 1 minus epsilon square by 2, 0 epsilon, 0. That is that Ry of matrix is this one. And this is the Rx of epsilon. When we multiply this to the first element is this 1 minus epsilon square by 2. And the second element is epsilon square. That is the second element. That is they are multiplying these two, this one. And here this epsilon and the epsilon will happen, that is epsilon square. And then the last element is multiplying this row and this column. And that is equal to, this is first 0, then 0. And here that is epsilon minus epsilon cubed by 2, that is a cube we are eliminating, that is therefore that is epsilon. And similarly, the second row element is 0, 1 minus epsilon square by 2, minus epsilon. And then last one is minus epsilon, and 1 minus epsilon square. And this is the matrix Ry into Rx. And from equation this 11 and 12, you can write that is Rx Ry minus Ry Rx is equal to, this matrix is the Rx Ry, and this matrix is the Ry Rx, and we are taking its difference. For the first, that is 0, and then we are taking the difference. This is minus epsilon square, and then epsilon minus epsilon is 0, and here this the difference is epsilon square, and then 0, 0, 0, 0, 0. This is equation 13. From equation 13, it is clear that if we limit the expansion of the sine epsilon and the cos epsilon up to the order epsilon, defined, then definitely RHS of equation 13 will be a null matrix. Here, if we will not take this in our expansion of the sine and the cosine, the epsilon square and its a higher order, then this quantity definitely goes to 0. That means this is a null matrix. That means at a very small angular rotation, operators are commuting. And this is the reason we initially said that if the angle is very small, if the rotation is very small, then the rotations will commute. And so the non-commuting nature of the rotation happens with an angle. The lowest order happens at epsilon square. That means in the order of epsilon, up to the order epsilon, and the two operations will converge. In the higher order, from epsilon square onwards, they started to deviate. And if you take angle is higher and higher, this quantity is large, and that is the nature. Now from equation 8, by the substituting epsilon is equal to epsilon square, we get, and we are going back to our equation of r z of epsilon. And in that equation, we are substituting, that is, we are taking equation of r z of epsilon. That is, r z of epsilon is we are taking. And this is the equation number 8. And here we are substituting epsilon is equal to epsilon square. And so here it will become as 1 minus epsilon raised to 4. And here this becomes epsilon square. Here also epsilon square. Here epsilon raised to 4. But here we are limiting up to epsilon square. Therefore, these the terms are taken as we are neglecting comparing to that one. Okay. So the r z of epsilon square is equal to 1 minus epsilon square 0 epsilon square 1 0 0 0 1. That is taken as equation number 14. And here also we eliminated the terms greater than epsilon square. From equation 14, r z epsilon square minus 1. This is equal to 1 minus epsilon square 0, epsilon square 1 0, and 0 0 1 minus this 1. This 1 is the identity. Therefore 1 0 0, 0 1 0, 0 0 1, and this is equal to this quantity. And from equation 13 and 15 we have, so we are taking that two equations, and Rx of epsilon Ry minus Ry Rx is equal to Rz minus 1, and this is equal to Rz of epsilon square minus Rne 0, and this is the one is taken as Rne 0, and where Rne 0 is the rotation matrix corresponding to any axis with a 0 degree rotation, and it is an identity operator. And that means the here R1 is the Rne 0, that is a rotation about any axis with the angle 0. And if the angle 0 rotations are no rotation, that means it is identity itself. And now we are going to discuss infinitesimal rotations in quantum mechanics. So far, that means so far we have discussed rotation of a vector in ordinary three-dimensional space. In quantum mechanics, the state of a system is represented by a vector in an abstract mathematical vector space called Hilbert space, and all the vectors that belonging in this space are possible state of the system. And that is our the quantum mechanics first postulate. That is our first postulate. In quantum mechanics, the state of the system is represented by a vector. In an abstract mathematical vector space is called Hilbert space. And all the vectors that belonging in this space are possible state of the system. Generally, this space is a complex vector space. It is a complex in nature. And when a system, that is a complex number space, that's one. That is when a system undergoes a rotation R in this space, the state of the system denoted as ket alpha undergoes a change and resulting a new state. And the resulting new vector can be expressed in terms of old vectors by the transformation operator corresponding to the rotation as alpha prime. This is the new vector transformed. That is the new vector. This is equal to d of r alpha. And here this d of r is called rotation D matrix. And here this the d come from German word Drehung, means rotation. That is a German word, first letter of that one. Therefore, that matrix, that means the rotation matrix in the quantum mechanics is termed as the D matrix. That's one. Nature of this the matrix that depends on the dimension of the space. In the case of a two-dimensional space, it is a 2x2 matrix. And example is a spin-half system. That will come in more detail in the coming section. And for a three-dimensional space, it is the 3x3 matrix. In the complex vector space also, the inner product is conserved. And so the nature of the matrix is unitary. Here, this is the rotation is only in 3 dimensions. That's in complex space that only, and therefore that rotation is unitary. And here, there is the unitary is the orthogonal equivalent in a complex space. That's only. Orthogonal transformation means that is the transformation in our ordinary space, and the unitary means that is the same. That is the same in a complex space. That only. If an operator U is said to be unitary, then U dagger is equal to U dagger U is equal to 1, where U dagger is transposed with the complex conjugate of U. Because that U, that matrix is maybe complex, and so that is when we are taking its U dagger, then it is we are taking transpose along with the complex conjugates. In the case of a real space or real number, that's a real space. And then only limited with the data transpose, because that all elements are real values. Here these values are maybe complex. Therefore, we want to take its complex conjugate along with the transpose. And if it is following this condition, that will be termed as a unitary. I think that you are already familiar with the properties of this unitary transformation and so on. Now, from the property of a unitary operator, that is, every unitary operator can express in terms of a Hermitian operator. We can write, this is a mathematical equation. Let's say we are taking that equation. Let's say any unitary operator we can express in terms of a Hermitian operator. And that relation is U is equal to exponential minus I epsilon G. This is the relation that connected a unitary operator and a Hermitian operator. And here this epsilon is a small parameter. I is the complex number, that is I is a root minus 1, and G is the Hermitian operator. Epsilon is a small parameter and G is the Hermitian operator. If epsilon is very small, then from equation 18 U is equal to exponential minus I epsilon G is equal to 1 minus I epsilon G, plus that we are using that expansion of that exponential, and that is nearly is equal to 1 minus I epsilon G, because that is we already said that is the epsilon is a very small quantity. Therefore, we can delimit with that first two terms, 1 minus I epsilon G. Here the Hermitian operator G is called as the generator of the unitary transformation. And here when we are writing in this equation, we are writing, and that the G is termed as the generator, because that creates or generates that transformation. In the case of rotation, the generator is the angular momentum operator J. And here that is the similar kind that you may be familiar. in the case of a translation, the generator is a orbital angular momentum, linear momentum. And in the case of a time translation, that the generator is our Hamiltonian of the system. And here it is the rotation, and so here the generator is a angular momentum. Hence, for an infinitesimal transformation of rotation from an angle d phi about the z-axis, the corresponding unitary operator from equation 19 is. That is u is equal to, that is this one, that is for an infinitesimal rotation d phi about the z-axis. The corresponding unitary operator is u, that is termed as, that is dz, our d matrix, that is about the z-axis, that is dz of d phi, that is equal to 1 minus I by h cross jz d phi. That is that one. This is our equation, that is equation 19, that is u is equal to 1 minus I epsilon g. And here, that is the g, that is the generator, and here for the rotation, that the generator is our angular momentum operator, and epsilon is a small parameter, and that parameter is an angle rotator. And so we can write it this way, and that is u is termed as a dz for this the unitary transformation, that is the corresponding unitary transformation. Here is a rotation, so it will be denoted as a d, and that is equal to 1 minus I by h cross that is a jz d phi. It is introduced in this. Okay, this is one. And here h cross is introduced in order to make the quantity dimensionless. Now, a finite rotation can be obtained by performing infinite number of infinitesimal rotations in succession. So, for a finite rotation phi, initially it is divided as n number of small rotations, and then angle rotated in each step is phi by n. Then this set of phi is equal to, we are taking that is limit n tends to infinity, 1 minus I by h cross jz phi by n all raised to n. This is equal to exponential, this way we can write, and that is expanded by using the expansion of that is exponential. This way we can write. And now we are going to derive general commutational relation for angular momentum. To obtain the general commutational relation for angular momentum, consider equation 16, that is this one. This is the equation corresponding to rotation in 3-dimensional space. And here is the classical rotation operator. You get the quantum mechanical commutational relation. Instead of taking r, we take d. And now take the value of d from, that's a former equation 22, and substitute it for r in above, we get. This is the d equation is 22. And substitute in here, and then we get this one. And this is a that is the dx, and this is dy, and this is the dy, and this is the dx, and this is equal to, that is right side is equal to 1. Here also we are the limiting up to the epsilon square, and now equate the coefficient of epsilon square on either side of above equation. Then we get, if you multiply this each term, and here if you first one is the multiplying all other, and then this the minus jy square divided by 2h cross square is the corresponding term. And so in each case we take these values, the corresponding, therefore its epsilon square coefficients are in these two multiplication, its values are minus jy square divided by 2h square, and this jy by h cross square, this is jx square by 2h cross square, and here this the corresponding terms are these, and this is equal to minus I jz divided by h cross. Or we can write it as this way, that is here this the terms are common, that here this is a minus, and this becomes j plus, and this will cancel out, and here also these two terms cancel out, and the remaining is this one. And or you can write is jx jy minus jy jx is equal to ih cross jz, or jx comma jy is equal to ih cross jz. The above equation is a cyclic in x, y, and z. That is jx comma jy is equal to ih cross jx, or jx comma jz comma jx is equal to ih cross jy. That is cyclic. This is the cyclic. And the general form of above commuter relation can be written as ji comma jj is equal to ih cross epsilon ij k jk, And this equation is called as a general angular momentum commutation relation. Here, value of epsilon ijk is +1 if ij and k are different and they are in cyclic in order. If any indices repeats, its value is 0. If any indices repeats, it goes to 0. And it is, if it is order values, it is not cyclic in nature. Here there is not, this is condition. That is not cyclic in order. Its value is -1. Okay. And now I'm going to discuss about this spin half the system and the finite rotations. And in this section, we examine the nature of a spin half system. In Cylindric experiment, when a beam of electron passes through a non-uniform magnetic field, which is along the z-axis, two spatially separated beam will result. So you familiar with that experiment? And this spatial separation is the resulting from 2 degrees of freedom or internal state of the system, and it is characterized by property spin. The 2 states are denoted as SZ plus and SZ minus, or more simply as a plus and minus. These are the 2 states. Now these the 2 states they can consider as the basis of our abstract 2-dimensional space, and using this we define the following Hermitian operators. And here, that means from our Cylindric experimental setup, we observed that there are the 2 kinds of beams, and one we termed as up and other is termed as down. That is on the basis of the direction of magnetic field. And so here we are saying that the spin has the 2 degrees of freedom. One is the up and the other is down. That will be denoted as plus and minus. And so that abstract space, and so we are considering an abstract space, and in that the space is the basis is taken as this plus and minus. And therefore from this the basis and or this the space that we can create some Hermitian operator, that is xx, xy and sz. These are operator, and just not this the operator. And here sz is the eigenvalue operator of plus and minus. And then you can check, that is just the substitute sz plus, and then you get is equal to plus h cross by 2 that itself. And if you sz minus, then you get a minus h cross by 2. That means simply you can check it. Do it as exercise. And if we consider these values of s as j, then we can found that it will follow our general commutation relations for angular momentum. Do it as an exercise. That is, you substitute its value, then you get if you can found that it will follow the general angular momentum computation relation. So this entity delivers a lowest dimension system which follows the general angular momentum relation. This intrinsic angular momentum property is termed as a spin, and it is not any kind of a spatial rotation. But here we will be found that this behaves as a spatial vector. That is the thing. So when we are taking the some operator in this abstract dimensional space, that is 2-dimensional space, and if we generated some operators, and this the operator will follow our commutation relation of angular momentum, that is general commutation relation of angular momentum. And so here we are termed it as angular momentum, and that will be named as a spin. It is a spin, and it is nothing a rotation in the space. That means if our this way of gesture is not correct, that is not a rotation. This is something different. Okay, but there is very interesting property it is. But here we can found that this behaves as a spatial vector. Okay, and this is the state. That's we are going to determine how it is. The state of the spin half the system is represented by a ket alpha. After rotation phi about the z-axis, the new state is alpha prime. So it can be represented as alpha prime. It is equal to dz phi alpha. And here this is the dz is the corresponding our rotation matrix, and here that's angular momentum is taken as sh. That is the rotation about the z-axis. Therefore, it can be written that way, 27. To determine the effect of this operation, we calculate the change in expectation value of sx. After this the rotation, this is a sx tends to sx prime. That is, we have to determine the expectation value of xx. after the rotation. That way we can write that is alpha prime Sx alpha prime. This is equal to alpha into d dagger phi Sz. That way we can write. And from equation 27, and this the d dagger is equal to this quantity, that is equation 29. And now the substituted value of Sx from equation 25 and 29 we get. So we are substituting its value. And then its final result is that is Sx cos phi minus Sy sin phi. And here this is the procedure, and this is procedure. This is the procedure, an icon, the state of this set. Therefore, Sz the icon is here. We get that is a h cross by 2. Therefore, that h cross will be cancelled, and then remaining is e raised to I by 2. And then we are the rearranging and by the taking expansion of a cosine sign. Then we get this is the quantity. And similarly, if you determine the Sx, then the result is this one. And then this is Xx, and therefore Xx is equal to this one. And similarly, if you determine Sy, then this is that quantity. And regarding Sz, then if you determine the value of Sz, that's the component is this one. And here, that means the corresponding is written in this. And here, this is exponential is, and this exponent of Sz itself. And this, we have the used factor with it, this one. Sz prime is. These are the three components right in the form of a matrix like this. And so when we are the check matrix, this is the transformation, and this is the same as the transformation matrix in our three-dimensional space. That is a very important property. That means even if the spin is the anyway not the related to a rotation in our ordinary space, but that is we found that it is able to deliver a rotation in space. Okay. And now, and this is an important property. And I am going to, before the concluding, the one more important characteristics is going to discuss. And this is one. This is an arbitrarily spin state. The alpha can be expressed in terms of basis the plus and minus as this way. And we can write this is the alpha is equal to, and the plus alpha, this is its component, plus, and this is its this component, and or alpha is equal to this way. That means this quantity is a scalar, plus alpha is a scalar, therefore you can write the second, therefore this one, therefore it will come in the form of an operator. And now we examine the effect of a finite rotation on this axis. We are examining a finite rotation, and here this act on here, and then we get this is the value, and exponential minus I phi by 2 this quantity. And now if we substitute phi is equal to 2 pi in the above equation, we get, and this is the nature. And so there is here there is a very remarkable property is that this is alpha of 2 pi is equal to minus alpha. That means after one complete rotation, the vector of the alpha reverses its direction. Now we perform one more the 2 pi rotation in the above state, it becomes alpha itself. So the symmetry of the spin half of the system happens only after 4 pi rotation above the axis. And you can just see it by simply by taking a strip of paper and it the round make it the round by the joining the two ends. At the time of the joining, just reverse its the direction. And then we are starting from the initial to a 2 pi rotation, then you reaching within that point, and that means it is negative. And again, if you are rotating 2 pi, then you can found that it is the come outside. So therefore, that is the nature of that spin. Okay, and so that's here I am going to conclude this one. So all contents are taken from this the modern quantum mechanics by 𝐻𝐠. Thank you.
Thank you, sir. That was a really refreshing session. Sir, for questions on the total, ഞാൻ ചോദിക്കാമോ questions എല്ലാം?
ചോദിക്കാം, പക്ഷെ ഞാൻ അവസാനം ഇച്ചിരി സ്പീഡ് ആക്കേണ്ടി വന്നു. വെച്ചാൽ അത് എനിക്ക് അത്ര എഫക്റ്റീവ് ആയി അവസാനം അത്ര ക്ലിയർ ആയി അറിയില്ല. ഞാൻ ചോദിക്കാം. ഓക്കെ, കേൾക്കാം.
Sir, vorticity and angular moment difference ആണ് ചോദിച്ചിരിക്കുന്നത്.
ഏതാണ്
ഡിഫറൻസ് vorticity and angular momentum?
ആംഗുലാർ മൊമെന്റം വേറെ ഏതാ ചോദിച്ചേ?
vorticity.
ക്ലിയർ ആവുന്നില്ല, ഒന്നുകൂടെ പറയാവോ? ഹലോ ഹലോ ആംഗുലാർ മൊമെന്റ് ക്ലിയർ ആയി, രണ്ടാമത്തെ ഏതാണെന്നുള്ളത് ക്ലിയർ ആയില്ല.
vorticity. അതെ അതെ.
ഓ അത് ഇതിനകത്ത് ഞാൻ ഡിസ്കസ് ചെയ്യാത്ത കാര്യമാണ്. എനിക്കത് അത് ഏത് കോണ്ടെക്സ്റ്റിലാണെന്നുള്ളത് ഒന്ന് ക്ലിയർ ആക്കേണ്ടി വരും.
സർ വേറെ ഒന്നും ചോദിച്ചിട്ടില്ല, അത് മാത്രമേ ചോദിച്ചിട്ടുള്ളൂ.
ഓക്കെ 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 ഓക്കെ, താങ്ക് യു.
സർ പിന്നെ വിഗ്നർ എക്കാർട്ട് തിയറം എന്താണെന്ന് ചോദിച്ചിട്ടുണ്ട്.
വിഗ്നർ എക്കാർട്ട് തിയറം നമ്മൾ ഇതിന്റെ അകത്ത് ഡിസ്കസ് ചെയ്യുന്നില്ല. അത് നമ്മൾ ഇതിന്റെ ആംഗുലാർ മൊമെന്റത്തിന്റെ കമ്മിങ് സെക്ഷൻസുകളിൽ ഡിസ്കസ് ചെയ്യുക. അത് നമ്മളിപ്പോ ഇതിന്റെ ഒരു ജനറലി അത് മോർ തിയറി നമ്മൾ അതിന്റെ അകത്ത് ഡിസ്കസ് ചെയ്യേണ്ടിയിരിക്കുന്നു. അതിപ്പോ ഇവിടെ പറയുന്നത് എന്റെ തിയറി നമ്മളത് അവസാന ഇൻട്രൊഡക്ഷൻ, അത് നമ്മൾ കമ്മിങ് സെക്ഷൻ്റെ അകത്ത് അത് ഡീറ്റെയിൽഡ് ആയിട്ട് ഡിസ്കസ് ചെയ്യും.
ഓക്കെ സർ, ഓക്കെ സർ. സ്പിന്നും
ഇൻട്രൊഡക്ടറി സെക്ഷൻ അത് ഡിസ്കസ് ചെയ്യണമെങ്കിൽ എനിക്ക് കുറച്ചും കൂടെ ടൈം വേണം. നമുക്കത് അത് ഡിറൈവ് ചെയ്ത് ഡിസ്കസ് ചെയ്യാൻ പറ്റുള്ളൂ.
സ്പിന്നും തമ്മിലുള്ള ഡിഫറൻസ് ആണ് ചോദിച്ചിരിക്കുന്നത്.
ഏതാണ്?
ഐസോസ്പിൻ.
ഐസോസ്പിൻ ആൻഡ്
സ്പിൻ.
Isospin, that is നമ്മൾ ഡിസ്കസ് ചെയ്തു ഇനിഷ്യലി. that is a clear, that is a isospin in quantum mechanics. That is a isospin is used to denote the multiplex. That means in the particle physics, when we are taking all the elementary particles as like not elementary, that means if you consider the case of a nucleon, and a nucleon consists the two parts, that is one is the neutron and the other is a proton. So therefore the neutron and the proton is considered as a two state of a single entity, that will be termed as nucleon. And that's similarly if you consider in the case of other particle like sigma, and sigma has three states, that is sigma plus, sigma 0 and sigma minus. And here that multiplies, that means its the properties behave the same as that of our angular momentum. That is the thing. That is the two are entirely different. It is not anywhere related to the spin of a particle. There is no relation.
So, how to measure orbital angular momentum in quantum mechanics?
So orbital angular momentum not discussed here. This is the general angular momentum theory. And now in order to write this the orbital angular momentum, we are taking the classical equation, that is L is equal to, we are taking R cross P, and then by the taking out the postulate of quantum mechanics, that means all the classical quantities are replaced by corresponding dynamical quantity, and then we got orbital angular momentum operator. That is the procedure. And here this is an introduction regarding general angular momentum theory. And this orbital angular momentum operator also follow over the commutation relation. That's the thing.
Distinguish between rotation of system and coordinates.
This is already here. I demonstrated that one. That means here, that is if you take this, we taken as the coordinate, and this is the x and y. And here if you take, that is means this is the v, say this the v is a vector, and say that this the v denote a system. So this is the state of the system, and so here we can rotate this the v, the some angle, that is the rotation of the system variation. And here but here if you change this the coordinate, that is the lab rotation, that is a coordinate that be termed as a passive rotation, and this be termed as an active rotation. That means that means in the quantum mechanics we are taking, that means the psi of r, and that is what we are changing is the psi itself. That means we are taking psi of r plus delta r. Not delta r, that is r into delta theta. That way we are rotating. That is the rotation of the system. Clear?
So difference between rotation of system and rotation of axis.
Rotation of axis means not clear. That means the system rotation means here this is in this the figure, that is this is the rotation of axis. Is it clear? That is just in our the discussion, that is we the mentioned a figure, that means xy coordinates, and then it is the rotated about the z axis, then it will be x prime and y prime, and that is the rotation of axis. Is it clear? That is the rotation of axis that will be termed as a passive transformation or passive rotation. And in the case of active rotation, that means that is a system vector. That means that the vector itself is rotating. That means an example I can say, and here this is the coordinate system, and here if there is a vector like this, and this the coordinate is rotating, at that side at the time this the vector remain unchanged. And that is the passive rotation or the rotation of axis. And if the vector itself is rotating, and that is the active rotation. That is the thing.
Hello, sir.
Clear ആവുന്നില്ല? Hello? Hello?
Passive and active transformation.
Oh, passive and active ആണോ ചോദിച്ചേക്കുന്നത്?
Yes, sir.
Passive active transformation means the transformation of a system. That is a system's transformation. That is active transformation. Passive transformation is a system of a coordinate. So we are transforming the coordinate, then that is the term as a active passive transformation. I think that this one, that is the last question, and these are the same. And here this is the, if you changing this the coordinate like this, and then this is the passive transformation. And that at that time this is the system here itself. And here if it is change the system, then that is the active transformation.
How to conserve angular momentum?
And the angular momentum you can conserve. That's in the classical way we can just say that is the conserve it by if there is the external torque, that is angular momentum is conserved. And here, but that is in quantum, coming to quantum mechanics, that is we are just saying that it is the conservation is come from commutation of this the angular momentum operator with the Hamiltonian. And that is the quantum mechanical way that the quantity is conserved. So any quantity, it is the commuted with the Hamiltonian, and then that the quantity is conserved. And here this angular momentum is conservation happens in quantum mechanics by following the commutation relation with the Hamiltonian. That is the thing.
So linear momentum and angular momentum തമ്മിലുള്ള ഡിഫറൻസും ചോദിച്ചിട്ടുണ്ട്.
So linear momentum means that is when a particle is moving in a straight line, that is a linear motion. It has an ability to impart a motion on another. That is the linear momentum. And angular momentum means that is a rotating object has the same thing. That is an ability to rotate the another, and that will be termed as impart a motion or the impart a rotation or tended to impart a rotation, and that will be termed as angular momentum.
Isospin spin value.
That means that is the thing. That is an isospin. That is we are using that the entity in entirely another context. Isospin is the denoting the multiplicity of particle. That is a multiplet different states of in a multiplet. Okay, but the spin is the not that is spin means it's the intrinsic angular momentum, and isospin not an angular momentum. It is not an angular momentum. And it is a quantity we are using to represent the different multiplex, different states, that is the different states in a multiplex. An example I already said, that means in the case of nucleon, that is the nucleon, we are saying that is an entity belonging in the nucleus. Nucleon, collectively. That is now we are knowing that it is the proton and the neutron. So we are saying that it is the neutron and the proton are corresponding to two states of nucleon. So we are here saying that this the nucleon, if the isospin is taken as 1/2, then that has the two orientations are possible. One is +1/2 and other is -1/2. And this generally sometimes the +1/2 is corresponding to proton and -1/2 is taken as neutron, or some others taken in reverse and so on. So it is not anywhere related to the angular momentum, but the property of this isospin is that to follow the mathematics of that commutation relation, that is general angular momentum. Okay, that is the importance of angular momentum in quantum mechanics. That is in introduction itself we said that it is the applicable to the property like the spin and isospin. But the isospin is not anywhere related to angular momentum. That means not a rotation. It is not a in ordinary spaces. Okay. എനിക്ക് തോന്നുന്നു നമുക്ക് ഈ സെക്ഷനില്ലാത്ത ക്വസ്റ്റ്യൻസുകളാണെങ്കിൽ അഡ്രസ് ചെയ്യാൻ എളുപ്പം. മറ്റേ ഞാൻ വിഘ്നറക്കാത്ത തീറൊക്കെ നമ്മൾ ഇതിന്റെ ആംഗുലാർ മൊമെന്റത്തിന്റെ കമ്മിങ് സെക്ഷനുകളിലാണ്. എനിക്ക് തോന്നുന്നു അത് നമ്മുടെ PG സിലബസിൽ തന്നെ ഉണ്ടോ എന്നുള്ളത് കഴിയുമ്പോൾ സംശയമാണ്.